Let's start. So, I made you a deal. I let you play hooky last Thursday for recitation, right? If what? If you know where you're going tomorrow ahead of time, you show up on time and ready to go. So no being late because it's the first day. So that was the deal that you can not go last week. So make sure you know where that is. It in this building? Is it Wexler? Okay. So after class, if you haven't, go find the room. Go find the room, and then make sure you're there tomorrow on time and ready to work. Okay. So let's just do a little overview R3. Which axis is this coming straight out of the board? X. To the right? Y. So there's our XY plane, right? It's the same XY plane that you've been living in your whole career, this one. Just rotated and flipped, or flipped 90 degrees and rotated 90 degrees, right? And then Z is up. Okay, so then what is the plane of the screen? What's the plane of the screen? What do we call that? That's the YZ plane, right? And then there is, what's the horizontal plane? The horizontal plane is? XY. And then the other vertical plane is? XZ, and it's coming like straight, you're imagining it's coming straight at you like that, right? Okay, cool. And then, so then we have octants. So the octants follow kind of the same pattern as the quadrants. Remember the quadrants? This is quadrant 1, 2, 3, 4. Same thing. So the first 4 octants are just like that, but above the XZ plane. So right now I'm showing the first octant, right? And to show the second octant, I'll be back in negative X territory. So that's in the second octant now. Corresponds to the second quadrant. Does that make sense? And then the third octant, there's the third octant, which would be like the third quadrant, lower left quadrant of XY. And then fourth octant is here. And then it's the same pattern, 5, 6, 7, 8, below the XY plane. All right, so I want to make X and Y positive. And then, so now this is the fifth octant. Fifth, sixth, seventh is below and behind and to the left. And then eighth is here. Does it make sense? So the coordinate planes break up space into 8 octants, right? 8 octants. Whereas the XY plane, you have 4 quadrants. Okay, any questions? And so then in your homework, oh, do you have your sheet? Just hold it at your desk. You got your sheet? Did you fill out? Okay, so hold it there for a sec because we want to look at it to talk. We talked about vectors in standard position. Remember, vectors can move. Vectors are mobile. It doesn't change the vector itself just by moving it. But there's a special place for vectors. And so that's when you put its tail. When you put its tail on the origin, we call this standard position. So this is special. So this is, right now, this vector is in standard position. What vector is it? 5, -4, -2. And so something special happens when you put a vector in standard position. What's special that happens? If I put the tail at 0, 0, 0, then what happens? Okay. You're talking about the tip of the vector? So the tip of the vector, what's the tip of the vector then? It has the same, its coordinates are same as the components of the vector. When you're in standard position, the coordinates of the tip are the same as the components of the vector. As soon as I move that vector, the components don't change, but the coordinates of the tip and the tail do, right? So this stays the same. If I move that vector, this stays the same, but the coordinates of the tail and the tip change. But they'll always be in the relationship of what? That the tip will be 5 greater in the x direction. The tip will be -4 in the y direction, and 2 in the z direction. This should be negative 2, sorry, negative. Okay, so does it make sense? Any questions about that? Okay, I wanted to you have the web work due tonight at 5. I want to do one problem from that, number 11. I did not show you how to. So our standard, at the end of class last time, we saw that our standard, based on the distance formula, we came up with the equation of a circle. And what we said was this is really, based on the distance formula, this is what? All points that are a distance of what? R, so the distances are away from what point? ABC, right? So ABC is a known point, and if you were to pick all points that were that distance R away from ABC, that would be your X, Y, and Z. So X, Y, and Z are variable, right? So X, Y, and Z are many, many points. A, B, and C is 1 point, and then R is our radius. Okay, so this is the most convenient way to write a circle because you can see exactly what the radius is and what the center is. But sometimes you get it like this, and so how do you get it from that form to that form? So very quickly, got to complete the square. So they've already gathered everything together for you. We've gathered the quadratic and linear terms of each variable. So to complete the square, you look at the linear coefficient. So your linear coefficients, 8, negative 16, and 14. You're going to take half of the linear coefficient and square it. So half of 8 squared is 16. So to complete the square, I need to add 16 for the x's. All right, half of negative 16 squared is 64. Half of 16 is negative 8. Squared is positive 64. So to complete the square for the y term, you need to add 64. And then for z, 49. Half of 14 is 7. Squared is 49. Okay, but whatever I do on the left, I have to also do on the right. So what am I doing on the right? Adding 16, adding 64, and adding 49. So now my equation still balances, still holds together, right? And now I've got my perfect squares. So these are perfect square trinomials. What is it? X plus 4 squared, y plus, or sorry, y minus 8 squared, z plus 7 squared equals whatever this is. But you know that it's r squared, right? Whatever that comes out to be is r squared. And so now you're home free. You just pick off the center and the radius from our convenient form of a circle, a sphere. Questions on that? Yes, please.
Why do you have a plus sign between x and 4 when it's x minus 8 in the equation?
It's x plus 8x, right? X squared plus 8x?
Well, I mean like the sphere equation that you wrote out and y.
Oh, right. Okay. So because these are, so how do we find the distance between 2 points? Remember? The distance between, yeah, so like if I had the vector, say 1, 2, and then 4, 5, we derive the distance formula by finding the magnitude of that vector. What's the magnitude of that vector right there? Square root of, what would it be? First of all, what is that vector? What's the components of that vector? It'd be 3 what? 3, 3, right? So where's the 3 come from? 4 minus 1, right? And where's the y come from? 5 minus 2. So that's why we do 3 squared plus 3 squared. What is that 3 squared? It's 4 minus 1, the x-coordinate of the last point minus the x-coordinate of the first point. That's why that's that. Better?
Well,
Yeah, so this is giving you the variation in x. The variation in x, the variation in y, variation in z is final minus initial. Better? Yeah. I mean, so these are the components of the vector, right? X minus a, y minus b, z minus c is a component of any vector from the center to the sphere. And so we're finding the length of that vector. Other questions? Okay, so you got you did your dot product exercise, and the whole point of that was to try to figure out make some generalization about given two vectors and its dot product, the value. What is that value? How does it reflect the two original vectors? That's what we want. This is going to be an important concept throughout the class. How does that final value of a dot product reflect something about the two original vectors from which it came? Okay, so let's just start with some observations that you made. All right, so what did you notice about in certain situations? When the vectors were like this, then I got a dot product like this. Yes, sir?
When they're at a right angle, then the dot product is 0.
Okay, so did you find that in the sheet when you were doing them? Whenever the vectors were at a right angle, and we call that orthogonal. So orthogonal's kind of a more general term for perpendicular. Perpendicular is like the geometric version of orthogonal. So orthogonal is, for our sake, you can just think of it as like perpendicular. Okay, but when you get into higher dimensions, you don't really have perpendicular anymore, but you have orthogonal. Okay, it's this kind of a similar situation. All right, what else did you discover here? Yes, sir.
Parallel vectors result in the highest values of the dot product, and anti-parallel vectors result in the lowest.
Okay, so when you have vectors pointing in the same direction, you get the highest value of the dot product. And what was that value? Did you notice what the value was? No, but just in general. What's that? Right. Okay, so when vectors have the same direction, the dot product ends up being the product of the magnitudes. Did every single vector have a length of 5 on that sheet? Or were there some that were different?
Yes.
Like in the bottom, weren't there any that were less than different than 5?
There's some that don't have like the bottom rows.
No, the magnitude of every vector is 5, though?
Yeah.
I need to change that. I need to change that because you really can't get this out of that. So what I need to do is change some of the magnitudes of those vectors. Anyway, this is what would happen if I did that. You would notice that if the vectors are in the same direction, then the dot product ends up being the product of the magnitudes. Okay? What other observations? And then he said if they're in opposite directions. The vectors are in opposite directions, what happens then? It's the opposite of the product of the magnitudes, right? So that's this. And then we said when they're orthogonal or perpendicular, the dot product is 0. Okay, now what other cases are there? So is there any other cases that we can talk about that you observed? Yeah, Cody.
There was like an acute angle, like the angle was really small.
Yeah.
It was close to the product magnitude, but not exact.
Okay, so we're talking about acute angles now. So they're generally in the same direction, but not exactly in the same direction. So acute angles. Then what did the dot product, how did it compare? It was,
Probably cosine, sine, 1 or 2, I was
but just in general, how did it compare to the product of the magnitudes?
less than.
Less than, right? Did you see that? That if one has a component in the direction of the other, like they're acute, then you get a positive dot product, but less than the product of the magnitudes. And then the last one would be going along those same lines. Obtuse. What would we get when we get obtuse? Negative, and then the value compared to the product of the magnitudes.
Greater than -8.
Yeah, so like less negative, right? Less negative than negative AB. So here, hopefully you made at least three of these or maybe more of these observations from going through the sheet. So then the question is, can we put these all together and make one general statement about what this number of the dot product is? Can we make one general statement about what this number is, thinking about how the original two vectors? So what do they all have to do with, first of all? We haven't talked about, okay. But this value, the value, right? The value of the dot product is, what is our reference point always? Yeah.
I you can kind of think of it as like absolute A times absolute B times cosine of the angle between the two.
Okay, but what is that? So what we're getting at is like, yes, okay, yep, you're on the right track, but that's just a formula. So we want to know, like, what is it? Yeah.
Like the growth of the original vector when the second one's applied to it, like how much it affects the first one.
Okay, all right, interesting. Other thoughts?
It's like a measure of how similar the directions are.
Okay, okay, good, nice, that's good. But that value, what is the common thing in all of these? The value of A dot B, the value.
The resultant vector will be how much of each vector is going in the same direction.
Product of the magnitudes. Product of the magnitudes. And every one of these, we're talking about the product of the magnitudes, aren't we? Yeah, or all but this one. So the kind of the common element here is that they all have to do with the product of the magnitudes. And when is it the product of the magnitudes? Exactly. Same direction. And when is it 0? It's like it's not at all product of the magnitudes. Perpendicular. So this goes back to what someone said. It's like how much. It's like the number is telling us how much they're in the same direction, right? Okay, so the value of the dot product is. It is the product of the vector's magnitudes. So that's what we want to think of it as. But there's a big but here, right? But what? It's like a certain degree of that, right? Like a certain extent of that, according to what? Yeah, and the relative direction is what? In the same direction, right? So like it's a product of the vector's magnitudes, but only as much as the vectors are in the same direction. How much are they in the same direction if they're orthogonal? They're not in the same direction at all. See that? So that's why you get 0. If they are in the same direction, you get the product of the magnitudes. And then if they're kind of in the same direction, right? You get something, you get like the product of the magnitudes, but like only as much as the one is in the direction of the other. So then someone mentioned, so what is that? As much as one is in the direction of the other. So it's kind of like so the dot product for this, it's not going to be that magnitude by that magnitude, but instead it's going to be like this magnitude times this magnitude, because that's to the extent that they're in the same direction. Do you see that? And so that's what you were saying. What is this right here? So if this is A and this is B, what is that amount of A in B's direction? How would we calculate that? It would be the magnitude of A, right, times what? Cosine of the angle between them. And then times B. So now I've just taken as much of A is in the direction of B. That's right there. As much of A is in the direction of B. And multiplied it by the magnitude of B. So this ends up being an alternate way of computing the dot product. Putting them tail to tail, you get this angle between them. Taking the cosine of the angle then takes how much of one is in the direction of the other. But it's still essentially multiplying the product of the magnitudes, but only as much as the one is in the direction of the other.
Did you use the y component?
Yeah, so there's no real x, y, and z here, but I think what you're saying is, could you take how much of B is in the direction of A?
Yeah.
Yeah, exactly. So this right here, whoa, got away from me. Oh, why did it do that? Anyway, why? This is all messed up. What is going on here? Yes. Anyway, how much? It's because my bearings aren't straight here. I'm tilted. So the amount of A in the direction of B is this times the magnitude of B would be the same as how much of B. So this would be how much of B is in the direction of A times the magnitude of A. You'll get the same thing. So it works both ways. Who asked that? Yeah, makes sense? Yeah, so you can, yeah, that cosine can join up with that, and then you're taking the part of magnitude of B in the direction of A, or it can join up with the A and then it's the other way. And you get the same thing both ways. Okay, so that's a really important concept, and we're gonna see that over and over again in the course. Okay, so we'll need that's exactly what we'll come to a situation. We'll be like, hey, we need this value, and then it's like, oh, that's the dot product because we want as much of this one. We want to multiply, but as much as they're in the same direction. So it's going to be an application for the dot product. So let's look at work. So we haven't done any work in this class yet. Do you know that? All right, so now we're going to do work. So work is defined as the total amount of force applied over a distance. We can investigate the amount of work to move an object by observing the force applied and the displacement vectors. Don't write word for word. You know, good note taking means your brain is on. You're abbreviating, adding stuff in that's not on the screen. So you're thinking. All right. So in general, work is calculated as. It's the amount of force applied over a distance. It's going to be force times distance. So that's our baseline formula for work. Force applied over distance. So we got this situation here. The girl's pulling a wagon with a force of 56 newtons, an angle of 39 degrees above horizontal for a distance of 8.1 meters. And we want to know what work did the girl apply to the wagon? So we can make a diagram here. So she's pulling with 56 newtons of force. And she's going to walk for 8.1 meters. So the first thing I want you to do is I want you to write vectors F and D in component form. If you have the standard, you know, positive X is to the right, positive Y is up. Can you write those F and D in component form, first of all? Could you do that? Hopefully. So that's hopefully something we can all do at this point. So let's see here. I'm going to learn your names eventually, but I don't have them yet. So how about this young lady in the black shirt here with the red hair? Can you tell me take your pick with the component of either component form of either F or D. Can you tell me?
For F,
0.56 for F. What do you think? Samantha, you agree with that? What would you say for F? Okay, so now the difference been offered up. What do you guys think? Samantha says 56 cos 39, 56 sine 39. Agree? So this is our 39-degree angle. For some reason I... Right, so the x component will be 56 cos 39, and the y component will be 56 sine 39. And then what about the vector d in component form? Tell me your name, sir.
William.
William.
It should just be 0 and then 8.5, 8.1.
0, comma 8.1. Agree with that? Other way around, right? 8.10. That's right. Okay, so there's f and there's d. Those are component forms of those two vectors. And so which component of f contributes to the work done, right? So all this force that she's pulling with, not all of that is moving the wagon, right? Horizontally. Which component contributes to the work done? X component, right? So it's only the part of the force that's in the direction that she's moving, the wagon, is going to contribute to the work done. So if we use our force times distance formula, then what's the force in the work formula? It's just going to be the 56 cosine 39. And what distance does she go? 8.1. So we get 352 joules. Force times distance. F 56 cos 39 times 8.1. So notice, work is the product of the magnitude of the force and the distance as much as they're in the same direction. Do you see that? So what's happening? What's going on here? So what is this, if you notice, what is this calculation right here? That's the dot product, right? So work is an application of dot product because you want only the amount of force that's in the direction you're going. That's exactly what we're talking about, right? So because of that, we could do it the other way too. So f cosine theta, magnitude of f, cosine theta, magnitude of d is f dot d. And so because it's the dot product, we could calculate it the other way too, like the way you did in the worksheet. You could do where you multiply like components and then add, right? What happens when you do that? You get the same answer, right? Because they're both the dot product. Multiplying like components and adding is the same as the product of the magnitudes times the cosine of the angle between. They're both the dot product. So remember, always remember, there are two ways to compute the dot product, and you'll get the same answer. So in a given situation, use the easier version. When you're doing work, when you're calculating work, it's totally legitimate to do this calculation versus finding the angle between them and doing this version, because you get the same number. Is the point clear? Does that make sense? So this meaning helped us to really see why work was dot product. Now that we know that it's dot product, we can use the other way if we wanted to calculate it. Okay, so example, how much work is done to push a box from point -210 up the ramp to the point P shown if the force applied while doing that is 8 -15 pounds? So where is -210 is maybe somewhere over here. And so we're pushing from here to here. So that's my displacement vector. And the force that we apply to do that is not exactly in that direction. It's 8, negative 15, 0. Generally in that direction. But when we push like that, for whatever reason, it slides up the ramp along D. So what's the work done? What's the work done to do that? So what, we got to find that angle in three-dimensional space. How are we going to do that? We got to find that angle in three-dimensional space. It's pretty hard, right? Pretty ugly. Daniel, you're shaking your head. You wouldn't do that. Don't we have to? No, why not? What can we do? F dot D. We got two ways to calculate that, right? Both give the same answer. Do we need to find the angle between F and this? Right. Don't do it. So instead, do what? What is F? F is my 8, negative 15, 0. D is? Negative 2, 1, 0 is D. That's the starting point. And the ending point is up here. So what's my vector D? Yeah, so I'm gonna do the displacement vector, right? It's gonna be negative 1, negative 7, 2. I like this way better. How about you? Yeah, trying to figure out what the angle would be in space. All right, so it's what, negative 8 and positive, what is that? Anyone got this answer yet? 105, so is it 97? Foot-pounds. 97 foot-pounds of work. Does it make sense? Now what if we wanted to find the angle? So now that I have that dot product, you know, the force is not exactly in that direction. The force is off in some slightly different direction than that. What if I want to find the angle between those two vectors? Is actually not that hard. How can I do it? Yep. Right. So now we know that 97 is what? Is the product of the magnitudes times cosine theta. Can we find that? Can we find that? Home free, right? So this is another application of dot product. You can use dot product to find the angle between vectors, right? By calculating it, by multiplying and adding components, calculating the individual magnitudes, and then all you've got left is your unknown is your theta. We won't do that, but I think you can finish that, right? Any questions? Yes, please. Oh, what's that? Where the 97? Where we got the 97? So the work is the dot product. Do you remember? So in the last we determined that work is the dot product of the F and D vectors. So I found the D vector by doing final minus initial. So this is D here. Negative 3 minus negative 2, negative 6 minus 1, and 2 minus 0 gives me the D vector. And then the force vector was given. So then I'm just computing the dot product by multiplying the components and adding, like you did on the worksheet. Is it better? Or where did I lose you in that? So it's 8 times negative 1 plus negative 15 times negative 7 plus 0 times 2. That's where the 97 came from. Is it better? Or did I lose you there? So the one way to compute the dot product is multiply the like components and then add those together. So I'm doing 8 times negative 1, negative 15 times negative 7, 0 times 2, and then I add, and that's the dot product. And we saw on the previous screen that the dot product computes the work if your two vectors are the force and the displacement. Okay, other questions? All right, so let's talk about projections. Projections. So there's a scalar projection and the vector projection of one vector onto another. So we're going to look at the projection of B onto A, B onto A. So the scalar projection would be, so looking at how much of B kind of projects onto A, the scalar projection is just then that length, right? It's just that length. So that's a piece of cake. What is that? So this is the scalar projection. So how would you compute that length? Pretty easy. So not the magnitude, right? The magnitude of B times cosine theta. So that length, the scalar projection, is magnitude of B cosine theta. Agree with that? But really, what is that? So now how can I use dot product to get magnitude of B cosine theta? How is that different from the dot product? There's no magnitude of A. So how could I write an expression that equals magnitude of B cosine theta? Yeah, so it would be the dot product, right? Then what? Divided by magnitude of A. So if you do the dot product, look, so here's a way of, the point is, here's a way of finding that length without the angle, without knowing the angle, right? So this is, the notation for that. This is the scalar projection of B onto A, is that length. How much of, what length of B is in the direction of A? And so it's A dot B divided by the magnitude of A. Okay, what about the vector projection?
Wait, what word is in front of A?
Comp, component, C-O-M-P, comp.
Oh, okay.
Yeah, sure. The vector projection then is that vector. So not just the magnitude anymore, but the vector. So we know its magnitude, right? A dot B over magnitude of A is its magnitude. And we know its direction. Its direction is in the direction of A. So this is a problem we've seen before. How do you find a vector in the direction of another vector at a specified magnitude? Remember what to do? What do we do first? Remember? Yeah. Find the unit vector in the direction of A. And then what we'll do is? Yeah, then we'll just multiply it by the length that we want, right? So we're going to scale A down to 1 and then scale it back up to the magnitude that we want. So how do we scale A to 1? Divided by the magnitude of A. So that just found a unit vector in the direction of A. And now how much do we want to scale that by? This, right? This is how much we want to scale that up by. So we're going to do A dot B. So this thing is scalar, and this is the vector, the unit vector in the direction of A. So notice we got two magnitudes of A in the denominator, so we can combine those. So we take the dot product divided by the magnitude of A squared, and we take that whole thing times the magnitude of A, or times the vector A. And that's that orange vector now. It's got the right length and the right direction. So that's, since it's the vector, it's the projection of B onto A. Okay, so again, the beauty of these formulas is that you can find that vector, or you can find its magnitude without knowing the angle, without having to find the angle. That's the point. Any questions? Yes, please.
I think my hardest part is just realizing what to do when to do it. You know what I mean? Like, what are like the key things that make you realize, oh, I need to do A dot B over to?
Because like here, notice that it's almost the dot product, right? So you keep in mind that the dot product was, it's just kind of having experience and noticing, oh, I know that this is the dot product, and that thing that I got almost looks like the dot product. There it is. So if I had this, how would I rewrite that then? It would be A dot B over magnitude of A. So that was just kind of recognizing, oh, look, I'm just the magnitude of A away from the dot product. So the dot product divided by magnitude of A. Is that kind of helpful? Yeah.
So if it asks for a scalar projection, you would put the comp A, B, and then if it wants the vector projection.
Scalar projection is the length. It's that amount of length. The vector projection is the actual vector. Yep.
So but the notation you would write it in.
Yeah, scalar projection is comp, and vector projection is for projection. Yeah.
This might be a little obvious, but I don't know. Scalar projection is no longer a vector, correct? After you do it, does it just give me a length?
It's a length, yeah. Right? Scalar projection is the length,
so
from there to there.
So vector projection will still have its magnitude and all that stuff. That's why we're doing it the way we're because it's just looking like we're just multiplying by scalar. So yeah. Thank you.
Yeah, vector projection is a vector. Scalar projection is a scalar.
Yeah.
Yep. So they're well named to help you remember. All right, so I think I summarized it here. That should be what you already wrote. If I didn't mess it up. How did I do? Is that what we wrote? Okay, good. Okay. So when it comes to these projections, in your homework, we haven't done lots of examples. So in your homework, it's kind of like you have to let's show everything here. So you kind of have to be on the lookout for situations where you're going to need these things. And maybe a clue is finding the angle will be very inconvenient. All right? So you just have to say, okay, now I've got these tools. the scalar projection of B onto A and the vector projection of B onto A. I got to remember that I have them and look for, in your homework, look for where you're going to apply it. Look for where you got two vectors and you need this length. Okay? Or you've got two vectors and you need that vector. And determining the angle is not helpful. Well, then this is where using these formulas are going to be really, really helpful. Okay, so how would we can you determine then, based on this, given what we've taught here, so can you write that vector? So suppose that so I want to. So really, what we've done there is we've we've broken B up into components such that one of its component is in the direction of A. Instead of using I and J, right? So like I and J would be like I along this, right? And then J like this. So the green one there is like breaking B up into its I and J components. But with projections, it's like you can take any direction and we can break B up into another set of components based on the, say, direction of A. Does that make sense? So my question to you is, can you think of a way that you would find this other component of B? So I just want everyone to think about it. So this blue vector is that's like the perpendicular component of B to A, as opposed to the parallel component, which is the vector projection. Vector projection is the parallel component of B to A. The blue one is the perpendicular component of B relative to A. How could you get that? How could you get that? Yeah, idea.
You do B minus the projection of B onto A.
Okay, so he wants to do vector B minus the projection of B onto A. So this has been offered up. Does it work? Does that equal, so I'll call it capital B for blue. Does that equal capital B? What do you think? If the orange and the blue are the components of B, components of the vector B, shouldn't use, right? Then what's the relationship between those three? What's an easy expression you could write between those three vectors? Yeah, Jose.
Can we do the Pythagorean theorem?
That would work for their magnitudes,
Yeah,
but what about for the vectors themselves? Yeah.
You're essentially treating A as sort of like a horizontal vector in this case. So by subtracting that projection, you're essentially removing that horizontal component,
Yep.
leaving only the vertical perpendicular.
So you're arguing this is right.
Yes.
Yeah, he's arguing this is right. Do you see it? So basically, when you have the components of a vector, so let's call the orange one capital A and the blue component capital B. Then what's the relationship between capital A, capital B, and little b? Yeah, so if it's the components, then capital A plus capital B equals little b, which would mean that capital B equals B minus capital A, and that's exactly what we said. So if you have the parallel component of a vector, then you can easily get the perpendicular component by knowing that's the missing piece, right? Those two components added together give you the vector, so you can subtract. Okay, so be aware of that in the homework as well, right? Be aware of that in the homework. If you need the perpendicular component of one vector to another, you could find the projection and subtract, knowing that those two components add together to give you that vector. Okay.